Hello and welcome to GED Live at PALS. Welcome to part 6 of important concepts in science that you need to know for the GED science test. Today we will have a look at a couple of chemistry concepts that are very important to know. So let's get started. With a quick overview, we will mainly look at atoms and bonding. And for that, we first need to have a look at the atomic structure. We will have a closer look at the Bohr model, and we will talk about elements, compounds, and mixtures. And in the end, we will look at chemical bonding and the types of chemical bonds that can form between atoms of different elements, specifically ionic bonds, covalent bonds, and metallic bonds. Okay, the atomic model. So we need a couple of basic understandings of the atomic structure and specifically the subatomic particles, the particles that atoms are made of. So the smallest particles of an element that still retain properties of the element are atoms, and which means basically the smallest amount of gold that you can have is an atom of gold. If you split the gold atom, you will have two atoms of different elements. So an atom is the smallest particle of an element that still retains the properties of the element itself. Atoms are made of three basic particles: protons, neutrons, and electrons. The protons and neutrons, as we can see on the left side, where we see an atom following the Bohr model, has a nucleus which contains the protons and neutrons, and then we have electrons arranged in shells or energy levels around the nucleus, in specific regions around the nucleus. The properties of these particles we can see here on the left side. Neutrons have a relative mass of 1 atomic mass unit, protons as well 1 atomic mass unit, and electrons have basically no mass. Their mass is negligible. It's very, very, very small compared to protons and neutrons, so usually it's fine to think as electrons having no mass, and protons and neutrons are the two particles that make up the mass of an atom. Another property that these particles have are charge. Neutrons have no charge, they are neutral. This is where the name comes from. The particles that have no charge, the neutrons. Then we have the protons, which are positive. Another way to remember that protons are positive is protons start with a P positive, P protons, and electrons then are the ones that are left over, and they need to be negative. So neutrons, the name itself comes from the neutral charge. Protons, P for positive, and electrons then must be negative. So again, here we see the Bohr model of the atom. This is what we will look at throughout this presentation and work with. We have a nucleus where we have the protons and neutrons. It's the positive charge center where all the positive charge is located in an atom, and it's as well the center of mass where all the mass of an atom is located. The electrons are present in specific regions, defined regions around the nucleus, which we refer to as electron shells or energy levels. No, they are actually not round shells like this, but they have different shapes, specific orbitals, but that would go a little bit too far for our presentation here. This atom is not to scale at all. The nucleus is in relation to the electron shells much smaller. Okay. Let's go to the next slide. Elements, compounds, and mixtures. An element is a pure substance made of only one type of atom. The number of protons in the nucleus is what's defining an element, and it's referred to as its atomic number, which we can see here. For the carbon atom, the carbon atom has an atomic number of 6, which means an atom of carbon will have 6 protons in its nucleus, and that's what's defining the carbon atom. If we would change the atomic number then we would have a different element. So every atom that has 6 protons is going to be a carbon atom. Elements can't be split into another substance by chemical or physical means. A compound is a pure substance as well, but this time it is made up of 2 or more different types of atoms, or 2 or more different elements chemically joined together in specific ratios. All molecules of a compound are identical in their composition. The ratio of atoms of different elements in a compound is fixed, and it can't be separated into its parts or elements with physical methods like filtration or distillation or something like this. We cannot separate a compound. Some examples of compounds here in the table below: ammonia and H3. So we have a fixed ratio of 1 nitrogen and 3 hydrogen atoms here. Or calcium hydroxide, carbon dioxide, fixed ratio of 1 carbon to 2 oxygens, copper sulfate, ethanol, which is alcohol, or glucose with a ratio of 6 to 12 to 6 carbon, hydrogen, oxygen atoms in a molecule of glucose. A mixture, on the other hand, is an impure substance. This time, that means that the mixture itself is made up of 2 or more different substances blended together. Mixtures of the same substances, mixtures of the same 2 substances can differ in their composition, in their ratio. For example, salt water, and we can have very dilute salt water, or we can have very concentrated salt water. And mixtures can be separated by physical means like filtration or distillation or evaporation. There are 2 major types of mixtures, which are homogeneous mixtures and heterogeneous mixtures. Homogeneous mixtures are even mixtures with a single phase, for example, salt water again, where the salt is evenly distributed within the water. It's dissolved. A heterogeneous mixture is a mixture that is not evenly mixed and usually has 2 or more phases. For example, a mixture of oil and water. Comparing mixtures and compounds: a mixture contains 2 or more substances. Compound is just a single substance made of 2 or more different elements combined together. In mixtures, the composition can vary. The composition in a compound is always the same. Of the 2 elements, they're combined in a fixed ratio. In a mixture, that's not the case. Mixtures, there's no chemical change that takes place when the mixture is formed. So if we use salt and water again, we dissolve the salt and the water, no chemical change takes place. We can separate the 2 again by evaporating the water, for example, and we get back the salt. Whereas when we have a compound and we react to substances with each other or to elements with each other, the substance that is formed is a new substance with its own chemical and physical properties. That brings us to the next point. The properties are those of the individual elements or compounds within the mixture. They don't change, whereas in a compound the properties can be very different to those of the component elements. The components may be separated quite easily by physical means, we mentioned that, whereas here the components can only be separated by 1 or more chemical reactions or chemical means. Okay, so 3 very important terms to understand when it comes to the basics of chemistry: what an element is, what a compound is, and what a mixture is. We will now have a closer look at compounds, because again, in compounds we have different atoms of different elements forming new substances. How that works is by these elements or atoms becoming more stable and forming chemical bonds. And that brings us to chemical bonding. So, why do atoms form chemical bonds in the first place? Atoms form chemical bonds to make the outer electron shell, or their valence shell, energetically more stable by interacting with other atoms. So here we have another key term already, valence shell. Later we will come to valence electrons as well. So whenever we read the term valence in chemistry, it refers to the outermost shell of an atom. So atoms form chemical bonds to make the outer electron shell, or valence shell energetically more stable, and this is done by interacting with other atoms. And this in return leads to usually a strong electrostatic force of attraction between two or more atoms, forming a strong chemical bond. Electrostatic forces of attraction are attraction between positive and negative charges. Opposite charges attract each other. You can think of it like in magnets, basically, where the south pole and the north pole of a magnet attract each other. The same is true for charges. Positive and negative charges attract. The octet rule is very important when it comes to atoms becoming energetically more stable. The octet rule is the rule of 8s. Atoms lose, gain, or share their outer shell electrons, the valence electrons, to gain a stable electron configuration with 8 electrons on their valence shell, on their outer shell. It's just an exception here. If the first shell is the outer shell, it is full and stable with 2 electrons. All other shells are stable when they are the outer shell with 8 electrons. In other words, atoms gain or lose electrons to attain an electron configuration of the nearest noble gas. Noble gases have naturally a full outer shell and are therefore stable on their own without any changes to the atom and electron shells. 2 examples down here. We have neon on the left side. Neon is a noble gas, and we can see that if we look at the outer shell, neon has 2 shells. Neon has 1, 2, 3, 4, 5, 6, 7, 8 electrons on its outer shell, so it's naturally stable. It doesn't need any change to its shell to be more stable. Oxygen, on the other hand, we can see here is 8 protons, 8 electrons in total, but only 6 electrons on its outer shell. That is 1, 2, 3, 4, 5, 6 electrons on the outer shell. And therefore oxygen is not in a stable state and when it's in its elemental form, and either needs to gain 2 electrons or share 2 electrons to get to its stable state. And there we already talk about 2 different types of chemical bonds that will result from either gaining electrons or sharing electrons. So the 3 options that atoms have to gain a full valence shell to become energetically more stable are either forming ionic bonds, covalent bonds, or metallic bonds with other atoms. And we see some examples of these over here, and we will now go into more detail on these. So ionic bonding. Ionic bond or ionic bonds form between metals and nonmetals. Electrons are transferred from the metal to the nonmetal and both get a full valence shell. Therefore, metals lose electrons and form positive ions. Now, this is something that is very often misunderstood because electrons are lost. We usually immediately infer from losing that's something negative, basically, in math, losing minus. So we immediately think, okay, metals lose electrons, so they become negative. That is wrong, because if we go back to our very first slide, if you remember what we've learned here, electrons are negative. And if we lose something that is negative, that means the atom itself now forms a positive ion because it has more positive protons than it has negative electrons. So the difference between protons and electrons will in the end determine the charge of the ion. If our atom has loses 1 electron, that means it has 1 electron less than it has protons, so it will be 1 positive charge. A nonmetal, on the other hand, will gain electrons because it gains negative charges. It will form negative ions. And in the end, the ionic bond results from strong electrostatic forces of attraction between the two oppositely charged ions that attract each other very strongly. Metals and nonmetals will react in specific ratios to balance the resulting charge on the ions. This is because different elements need to gain or lose different numbers of electrons to gain a full outer shell. Every ion in an ionic compound will have a full valence shell in the end. Now, that is very important. That's why we often need different ratios of atoms to achieve that. On the right-hand side, we see a few of these examples. Sodium, for example, has 1 electron on its outer shell. As we can see here, chlorine has 7 electrons on its outer shell. The easiest way for sodium to become stable, it is a metal, it has to lose its 1 electron, and then the second shell on the inside, as we can see, is going to be the valence shell, the outer shell, and it already has 8 electrons. So after losing that 1 electron, sodium will be electrostatically stable in terms of its valence shell. The chlorine atom will gain the electron that's lost by the sodium and itself becomes stable. We now have a positive sodium ion and a negative chloride ion which attract each other, and the compound sodium chloride NaCl has formed, where the ions are present in a 1-to-1 ratio. Magnesium oxide, very similar. The difference here, however, is that magnesium has 2 electrons on its outer shell. Oxygen, on the other hand, has 6 electrons on its outer shell. Magnesium wants to lose its 2 electrons, and oxygen wants to gain these 2 electrons. Again, magnesium oxide, we have the ions in the end in a 1-to-1 ratio, or the atoms reacting in a 1-to-1 ratio, because the 2 electrons that are lost by magnesium can be taken or picked up by 1 oxygen atom. We get a magnesium ion with 2 positive charges, an oxide ion with 2 negative charges, and the formula of the magnesium oxide compound is MgO. Very similar with lithium and fluoride, basically the same as we see on top. Lithium loses 1, fluorine gains 1. Now here we have the special case that lithium is now stable with 2 electrons on its outer shell because that is the first shell. Again, 1 positive, 1 negative charge. They attract each other. Lithium fluoride compound LiF. We don't see any charge here because, as you can see, the charges of the oppositely charged ions, they always cancel each other out in the compound itself. Lithium sulfide is a different example, which gets a bit more complex. Now we have sulfur with 6 electrons on its outer shell. It wants 2 more. Lithium just wants to lose 1, which means for every atom to gain a full outer shell, we now need 2 lithium atoms, each losing 1 electron, sulfur gaining these 2 electrons, and we now have lithium sulfide with 2 positively charged lithium ions, each 1 positive charge, and a sulfide ion with 2 negative charges. So the formula of the lithium sulfide compound is Li2S. Covalent bonding. Covalent bonds form between non-metal atoms. Non-metal atoms share electrons to gain a full valence shell. A covalent bond itself is a shared pair of electrons between 2 atoms where each of the atoms contributes 1 of the electrons to the bond. The shared pair of electrons counts for the valence shell of both atoms involved in the bond. Single bonds are 1 shared pair of electrons between the same 2 atoms. A double bond are 2 shared pairs of electrons between the same 2 atoms, and a triple bond are 3 shared pairs of electrons between the same 2 atoms. This is the highest number of shared electrons we can have between 2 atoms, 3 from each, so 6 in total, a triple bond. The atoms in the end bond together due to the strong electrostatic forces of attraction between the positively charged nuclei of the bonded atoms and the negatively charged electrons they share. Here we have a general example. We have 2 unpaired atoms, which are 2 nonmetals. Second one could be a metalloid as well. A few elements are metalloids, which have properties between metals and nonmetals. That's where they're located on the periodic table as well, between the metals and the nonmetals. And we can see that these two atoms bond together by sharing a pair of electrons, and now these two electrons count for the outer shell of both atoms, and when we count, we see we count for both of them 8. And that gives us a covalent molecule or covalent compound. Some more examples. As we already said, we have the single bond, the double bond, the triple bond. Here we see one shared pair of electrons between the same two atoms, two shared pairs of electrons and carbon dioxide between the same two atoms. Here a double bond and here a double bond again. We can see for carbon, which has usually 4 electrons on its outer shell, it shares all of its 4 electrons, and we count 1, 2, 3, 4, 5, 6, 7, 8 electrons for carbon. For each oxygen, we count 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. All atoms are stable in terms of the octet rule in this example. Same here. Nitrogen forms a triple bond with itself to form an N2 molecule, and we see both nitrogen atoms have a full outer shell. They fulfill the octet rule with 1, 2, 3, 4, 5, 6, and then 7, 8, or 7, 8 here on the other nitrogen atom. Covalent bonds can form different types of molecules based on the orientation of the bonds in an atom. In a molecule, in the end, we can see a polar bond as an example here, or a non-polar bond here, where in a polar bond our molecule has like a positive region and a negative region, although this is wrong here. Around the oxygen should be the negative region, and around the hydrogen the positive regions of the molecule. Non-polar bonds are even bonds, basically, where we do not have something like these positive or negative regions. And a coordinate bond is a special type of covalent bond where the two electrons that are shared come from the same atom. So usually a covalent bond, as we stated here, is a shared pair of electrons between two atoms where each atom contributes one of the two electrons shared to the bond. In a coordinate bond, both of the electrons that are shared come from the same atom, as we can see here. These two electrons come from oxygen, forming that triple bond here. So a few more examples. Chlorine forming Cl2. We have one shared pair of electrons. Oxygen forming O2. We have a double bond here with 2 pairs of shared electrons. Nitrogen, we already saw that, with a triple bond, 3 shared pairs of electrons between the same 2 atoms. And here HCl, hydrogen chloride, with again 1 shared pair of electrons. Again, hydrogen being special, only having 1 shell, which means it is stable with 2 electrons on its outer shell. So 1 covalent bond for hydrogen is enough to become stable in terms of its outer shell. The last type of bond we will have a look at are metallic bonds. Metallic bonds form between metal atoms. Metal atoms lose their valence electrons and form positive metal ions that arrange in a lattice structure. The lost valence electrons remain in the space between the metal ion lattice as delocalized electrons, forming a cloud or a sea of free movable electrons. The metallic bonds are very strong electrostatic forces of attraction between the positive metal ions arranged in the lattice and the cloud of delocalized electrons between the positively charged metal ions. So the electrons stick around in this case, but they're not really in the shells anymore. They are in the space between the metal ions. And we have only positive metal ions in the metal. There are no negative ions. The bonding works, positive and positive repels, but it is attracted with the negative electrons that are floating around between the positive metal ions. So some examples: sodium having 1 electron in its outer shell. Every sodium atom will lose 1 electron, and that electron becomes delocalized and moves around between the sodium ions. Magnesium having 2 electrons on its outer shell will lose its 2, forming 2 positively charged magnesium ions with more delocalized electrons in the metal. Aluminium, being in group 3 in the periodic table, loses 3 electrons to get a full outer shell, and these forming 3 positively charged aluminium ions with even more delocalized electrons now in the positively ion metal lattice. That's it for the types of bonding. I hope you have a better understanding of how bonds work between atoms, how different types of substances can be explained in terms of the bonds, and a general understanding about the atomic structure and some of the basic definitions that we need to know for chemistry, specifically elements, compounds, and mixtures. If you like this presentation, if you like this video, please consider subscribing to our YouTube channel. This will definitely allow us to reach more people like you who want to prepare for their GED exams. And yeah, I hope to see you for my next video, Important Concepts in Science, Part 7. Until then, see you next time. Goodbye.